You have some you can verbalize for me?
I can. Let me just pull it out here real quick.
Okay.
All right. So we got 3 to the 5/3 power times 3 to the 1/3 power. It's right now we're just working on like adding, subtracting.
Right. The
And
rules of exponents.
yeah.
So when you're multiplying the same bases, different exponents, what do you do to the exponents?
You just add the exponents.
Correct. So this answer is
3 to the 6/3, which is 3 squared, which is 9.
okay. What else you got? Let's just cover the three situations.
Right.
Okay. Tell me what this is. In other words, that was multiplication. This is division. What's that equal to?
2 to the 3rd.
Okay. And there's only one other situation, and that's this one where you have double exponentiation. What is that?
Multiplication. So you
Two
get 2 to the 12th.
2 to the 12th. Okay. So none of these should give you any problems at all, as long as you know those three rules. What else you got?
So parentheses 10 to the 1/6 times 10 to the 1/2, all that to the 12th power.
Don't really need that inside parentheses there.
Yeah, I was meaning parentheses around the quantity.
Ah, okay. I was going to say, I'm surprised they put that there. Okay, so what's our first step?
So you want to find a common denominator between the exponents.
Okay. In other words, our first step is to do what's inside the parentheses.
Yeah.
What is that going to equal? What's
so
10 to the 1/6 times 10 to the 1/2?
So you'd have to find a common denominator for the 1/2, which would be 6, so you multiply it by 3. So you'd get 3 over 6, so you'd have 10 to the 4/6. Sixths.
Which is the same as 10 to the 2/3.
2/3, yep.
Now what?
And then you distribute the 12, or multiply the 12, so you'd get 24 over 3 for the exponent.
Instead of doing it 24 over 3,
It's
I'd
8.
like to see you simplify it first.
8.
In other words, make that a 4, make that a 1, and now you got 4 times 3 to get your 12. You're going to get the same answer. Whoops, excuse me.
It's 8.
Yeah, 4 times 2. Sorry, I misread my writing. You're always going to get the same answer. The advantage of doing it my way is you deal with smaller numbers. Notice that the biggest number I dealt with was 12. The biggest number you dealt with was 24. So if you have a choice in math, always deal with smaller numbers. And what that usually means is reduce first. Okay, what else you got?
5 to the 1/6 over 5 to the 7/12.
Okay, what's that going to be equal to?
That's going to be equal to 5 to the negative 5/12.
Correct. And they
So it'd be 1 over 5.
At some point, they're going to tell you, always give your answers with positive exponents.
So you need to flip it to the denominator.
Right.
It'd be 1 over 5, 1 over 5 to the positive 5/12.
Right. And you can flip that either way. In other words, if I had something like the following, I can move that to the other side of the fraction bar like that.
Mm-hmm.
In other words, it's not just numerators with negative exponents that you can move to the bottom. If you have denominators with negative exponents, you can move them to the top and change them to be positive. Basically, that's what negative exponents mean, is reciprocal. Now, they don't really expect us to do anything more with this. You'd have to go to a calculator. You understand what 5/12 means?
Yeah, so it's the 12th root of 5, that quantity, to the 5th power.
Yeah, in other words, if I wanted to write it with a radical sign, I'd write it like that. Not that I ever would. I prefer fractional exponents to radical signs all day. And one of the reasons is that when you get to calculus, the most key thing is the exponent. So anything that has a radical sign in it, you change to fractional exponents immediately. What else? Let me cover two other rules that you may or may not come across. In other words, here we have different base, but same exponent. So what's that equal to? Without doing the math. In other words, what it's really equal to is 3/4 squared. Those two things mean the same.
Mm-hmm.
Same thing as if I have 3 squared times 4 squared. Again, different bases, but same exponent. So I can multiply the bases and I end up with 12 squared. Those are the only 5 rules I know with exponents.
Mm-hmm.
All right, what else you got?
Sheet here. It's mostly just like a lot of repetition of like mostly the same stuff of that. It's just using the rules of exponents with rationalized or simplified radicals.
Let's do one or two of those.
Okay.
At least one or two of them. In other words,
Yeah.
it sounds a little different than the previous ones.
Yeah, so it's basically just what we've been doing the past couple ones is what I mean. So 125 to the 1/3 times 64 to the 1/3.
125 to the 1/3. Oh, in other words, it immediately gives you the rule that I was just talking about.
Not 1 over 25, just like the 125.
Oh, 125. Okay.
Yeah.
Now, notice this is exactly what I was referring to. Different bases, but same exponent.
Mm-hmm.
So I can write this 125 times 64 all to the 1/3. Now, I don't need to write it like that. That actually makes it harder because they gave us these numbers that are perfect cube roots. What's the cube root of 125?
5 and
The cube root of 64.
4.
So that's 20. That's the best way to do it. If I do it this way over here, I got to get out a calculator and do both the multiplication with a calculator and then find the cube root of that 4-digit number with a calculator. So whenever you have a perfect cube number like they do here, always do this first. Okay, if I were to make that, say, 126 and 65, well, now the only way to really do it is the way I did it. Multiply 126 times 65 and then take the cube root of that on your calculator. And then round off, as opposed to taking the cube root of 126, rounding off, taking the cube root of 65, rounding off, and then rounding off again. In other words, whenever you're going to be rounding off, always round off at the end. Try not to round off mid-problem, because you're going to end up with a round-off error usually. And you may actually miss the answer by 1,000th or something. Okay, what else?
Three to the 3/4 times 2 to the 1/4, quantity to the 4th.
All right, now notice that we really can't do anything with the inside yet. In other words, I've got different bases and different exponents. So had you not given me this, the only way I could have solved this was with a calculator. And I would have just had to find 3 to the 3/4 and multiplied it by 2 to the 1/4. The fact that the whole thing is to the 4th power, now we have double exponentiation going on. So I can actually multiply that 4 by each of these exponents. In other words, that's the same as this. You can always separate that out. Times 2 to the 1/4 to the 4th. And notice what that does. It gives you a big advantage. What's this become? In other words, what is 3 to the 3/4 to the 4th power? Multiply x.
Oh, by multiply by the 4. Okay, so that becomes 12 over 4. It's 3, so it's just cubed. So that's 27.
Times what?
2.
So we get a nice round number doing it the correct way. If you'd have done this in a calculator and you'd have come up with that number, and you'd have come up with that number, and then you'd have taken that product and taken it to the 4th power, I'll bet you would not have gotten 54. There would have been some round off error there. None of these things are going to come up to be even numbers. In other words, 3 to the 3/4 power is not a rational number. So nor is 2 to the 1/4 power. That's not a rational number either. So you're going to get a decimal with like 12 decimal places for both of these numbers. And when you multiply them together, I'm not sure what your calculator would do. And then when you take it to the 4th power, it's going to round off that round off error even worse. And I'd almost bet money you do not get 54. You might get 53.98 or 54.03 or something like that. So you always want to do these problems, if you can, in a manner that leaves you with integers. In other words, by separating it into this, now it gives me nothing but integers, 3 cubed and 2 to the 1. So there's a huge advantage in doing it this first way. Okay, what else?
Let's do 60 to the 3/2 over 12 to the 1/2. 60. Sorry.
60 to the 3/2 over 12 to the 1/2.
Yeah.
Like that. Okay, this is interesting. That's different bases and different exponents. You sure that's the problem?
Yeah.
60 to the 3/2 divided by 12 to the 1/2. Well, let's see. I guess I could write this as the square root of 60 cubed divided by the square root of 12. And now I can turn that into, since it's square root on top and bottom. Go ahead.
Can't you just simplify 60 and 12, because 60 divided by 12 is 5, and you can subtract the exponents?
No, here's the problem with doing that. If I factor the 60, no, you're absolutely correct. As long as I put it into parentheses. Yeah, now I can deal with that. Very good. So that's 5 times 12. That's the answer. Excellent, Cole.
Thanks.
What else? I had, just for the heck of it, I want to show you these problems I got from, I don't know, that's honors geometry, but they were still some really good problems. I'm wondering, let me think for a moment, who did I get that from? I got it from Allie. All right, here. Let me just show you some of these. These might be a little more challenging, actually. If you're out of new ones, that last one you gave me was kind of a new one, worth doing. So if you have new ones, we'll continue on with your problems. But if you run out of problems and you're looking for some interesting problems, these are kind of interesting problems here. You can see that it's very similar stuff. So let me just hold on to that for a moment. And I always want to make sure we do your stuff if you have stuff to do. What else you got?
I think that's pretty much it. That's pretty much just all the general types of problems.
So there's nothing, in other words, that last problem was quite different because it was different base to a different exponent divided by different base to a different exponent. But we were able to factor the 60 and turn it into, notice that I made a mistake.
Yeah, so you can factor the 12 cancel. Yeah, so
in other words, that 3/2 has to be applied to the 5 and the 12, and then the answer does not equal 60. It's whatever that number is, and you'd have to get that out of a calculator. Interesting. Why would they give you that problem? Because if I had to use a calculator, I could have done it like that.
The way that my teacher explained that we do these is that pretty much it acts, you put the 60 in parentheses outside and the exponents outside, the 12's in parentheses, the exponent outside. You simplify the 60 and the 12 into 5, and then you subtract the exponents.
Right, and that's what I did, and I made a mistake when I did it. In other words, here's what I did.
So you end up with 5, and
that's what I did. In other words, I just separated the 60 into two different numbers, both with the same exponent, and now I've got, in fact, did I do it correctly even the second time? I'm not sure I did. Times 12 to the 3/2 over 12 to the 1/2. That's the answer. And then this simplifies to 12 by subtracting the exponents. And this you get out of a calculator. Am I missing something? I think that's what you have to do.
Like, no, so
In other words,
how it was explained to me is that the 60 and the 12 reduced to 5, and you subtract, so it's 3 halves minus 1 half. So it's 2 over 2, which is 1.
I don't think you can do it that way, to be honest with you. In other words, what you're saying is that the 60 is 5 times 12 to the 3 halves. And now you're saying you can subtract the exponents. You can't really right away. In other words, you can't really. The only way you can subtract the exponents is if the bases are the same. And 5 times 12 is not the same as 12. But once I split it up into two fractions, in other words, I've got 5 to the 3 halves divided by 12 to the 1 half. Oh, okay. No, I did it correct the second time. I don't know what's wrong with me. All right. So the final answer is that. And 12 to the 3 halves and 12 to the 1 half becomes 12. But I still have to multiply it by 5 to the 3 halves. Hold on 1 second, if you would. I'll be back in a jiffy. The salesman, I'm sorry. I usually don't answer the door when I'm in a session, but I have a student that I thought maybe was here an hour earlier than his regular appointment. All right, I don't want to leave this problem because I've really screwed up on it. Let's do it from the beginning. 60 to the 3 halves divided by 12 to the 1 half. Okay, I can split that into 5 to the 3 halves times 12 to the 3 halves, correct? That's the numerator. And then the denominator is that. And now what I'm going to do is turn that into 12. So my answer has to be 5 to the 3 halves times 12.
That makes sense.
And that's the proper way to do it. Now,
that makes sense.
Like I said, I still have to go to a calculator. I guess that's simplified. It is. But I don't know what that number is. It's some irrational number that I would have to go to a calculator. And if I'm going to a calculator, might as well do it directly from there. So in other words, it doesn't reduce to an integer. All right. We don't have much time. Let me give you one of these other problems that I encounter. Let's see if I can find an interesting one. There are a few interesting ones here. Number 13. We'll just start there. We got 4 root 6 times, hold on. All right, we got 4 root 6 times 3 root 15. How do I do that?
1 second. Little meeting thing's just in the way. I'm just moving real quick. It's been so long since I've done this.
Well, here, let me tell you how to do this one, and then I'll give you a more interesting one, 15. You multiply the numbers, 12, you multiply the insides, root 90, and then you simplify. What's root 90? Well, 90 factors into 9 and 10, so I end up with 12 times root 9 times root 10, and root 9 becomes 3, so I end up with 36 root 10.
Okay.
And that's your final answer. That's how you do that one. Now, a more interesting one is 15. 12 root 14 times 7 root 21. Now, notice that if I use the same technique, I'm going to multiply 14 times 21 and then take the square root of it. Or try to factor, try to simplify it. And that's going to be hard. When you're trying to simplify big radicals, you know, if I give you a big radical like this, that's hard to simplify because you have to find factors of that big number. So it's very difficult. So it's easier if I factor this separately and make it 12 times root 7 times root 2. Normally I wouldn't do that because neither one of those pull a number out. But now if I make that 7 root 3, now notice I can combine those two. Root 7 times root 7 is 7. So I end up with 12 times 7 times another 7 times root 6. And that ends up much easier because I still have to go to my calculator to do 12 times 7 times 7, but it's certainly easier to multiply in a calculator than it is to try to find factors. So there's a big disadvantage in going the original way by multiplying those two numbers, because now I got to try to factor that big number. As opposed to if I factor it first into 7 and 2 and 7 and 3, now I can combine the root 7 times root 7, which is 7, and makes the problem a lot easier. So same line of thinking as what your stuff is, just a little different step to it.
Yeah.
All right. Is Monday still the best day for you, Cole?
Yeah, it is. I just didn't have any material on Monday, so it was just not worth.
Yeah, I get it.
Having a session.
That's great. I love Monday at 3:30. Works for my schedule really well also.
Yeah.
I will talk to you next Monday.
All right. Talk to you next Monday.